Welcome to our Introducing Web Sketchpad workshop. Web Sketchpad originated from the Geometer Sketchpad, but has been redesigned and recoded from the ground up, with the objective of providing the simplest and most intuitive interface possible for a dynamic mathematics web app. It integrates tightly with web pages, providing for two-way communication between Web Sketchpad and the web page. As you see on the left, we've eliminated menus, unneeded tools, and most dialog boxes, and instead created widgets that support many operations for which you used to need menus and dialog boxes. We'll ask you to try out your first web sketch in a moment. To do so, please go to the website listed here on the bottom of the page, so you can follow along with us during the workshop. Please pause this video now and restart it once you have the website showing in your browser. Now that we're on the same page, let's take a look at a sample Web Sketchpad activity. This is a warm-up activity in a lesson introducing students to transformations by treating them as functions in a geometric context. By addressing functions in geometry, the lesson uses the unfamiliar territory to spur students to think about how to distinguish between independent and dependent variables, to observe closely the relative motion of the two variables, and to notice fixed points and other features they might not ever think about in a context based on numbers and formulas. Please pause your video now, experiment with the sketch for a few minutes, and then restart your video. Welcome back. You probably noticed that you can drag point A, but not point B, suggesting that A is an independent variable and B is not. The two hint videos here are short silent movies that show you how to use the style and trace widgets. You'll learn a lot more about Web Sketchpad in the rest of this workshop, which consists of pairs of topics. The first pair, parts 2 and 3, addresses Web Sketchpad's innovative approach to tools using a consistent self-scaffolding paradigm that simultaneously allows tools to be tailored to each web sketch and even to each page of a web sketch. The second pair, parts 4 and 5, present a deeper dive into two areas of particular mathematical and curricular interest: promoting students' deeper understanding of functions by integrating them into students' geometric experiences, and using transformations to enhance students' experiences with proof in general and congruence proofs in particular, culminating in a constructive proof of the side-side-side theorem. The third pair, parts 6 and 7, highlights Web Sketchpad's support of important pedagogical practices, its relationship to cognitive science research, the web-based support that makes it a valuable learning tool for both in-person and virtual classes. Thank you for participating in this workshop. We welcome your comments, and we encourage you to post your questions, comments, and suggestions on this blog site, which will be devoted to reactions from participants and our responses to them in support of this workshop. Thank you for your attendance.
Web Sketchpad is designed to make it easy for students to use construction tools. Each Web Sketchpad model comes with just a small set of tools, allowing students to focus on just those tools that they'll need for the construction at hand. Here is a web sketch that students can use to construct the ortho center of a triangle. Recall that an ortho center sits at the intersection of a triangle's altitudes. Let's explore how to construct a triangle and its ortho center. I have 4 tools, and I'm going to use the segment tool to construct my triangle. I'll tap on the tool icon, and I see a preview of the segment that I'm about to construct. I can tap on the screen check mark and place my segment in my sketch. I can now drag its endpoints. I'm now going to back up a step to show you another way of constructing the segment. Again, I'll tap on the tool icon, and notice that the left endpoint of my segment is glowing. That indicates that this endpoint needs to be placed. I'm going to click and drag it and move it over here, and now I notice that the other endpoint of my segment is glowing, so I'm going to click and move it over here. And again, I now have my completed segment. For my second side of my segment, I'll tap this tool icon again, and I need to place this glowing point. And rather than drag it, I'm going to just tap where I'd like it to go. So I'd like to merge this point with this endpoint. So I'll tap, and my point scoots over, and they merge together. Now this endpoint is glowing, so I'll tap here to place it. And now I have two sides of my triangle. For my third side, I'll create another segment, and I'll tap again, and I now have my completed triangle. Let's look at a slightly more convenient way to construct a triangle. Since I'm constructing 3 segments in a row, I'm going to double tap this icon to keep the segment tool active. So now I'll tap and tap to place my first segment, and I'm immediately given a preview of my second segment. So I'll tap, and I'll tap again, and for my third side, I'll tap, and I'll tap. And I'll then tap on the X to close the tool. And here I have, well, I expected to have a triangle, but there's a little problem here. These two endpoints are not attached. So you might think that I would need to back up and fix this, but in fact I don't. Web Sketchpad has a feature called drag merging, which lets you fix any of your so-called mistakes without having to back up. So if I take this endpoint of my segment and I drag it on top of the other endpoint, that point will glow and I can let go, and these 2 points are now merged, and my triangle is good as new. Now, there's also another way to construct a triangle, and that is using my third tool here, which if I tap on it, I see a preview of the entire triangle at once, with the interior glowing. And if I just tap anywhere in my sketch, the entire triangle gets placed, and I'm ready to work with it. Now I should also point out, if I back up a step, that if I tap on this tool and I don't want to place the entire triangle at once, I can instead drag a vertex of my triangle, and Web Sketchpad is smart enough to now know that I want to place the remaining 2 vertices. So I can tap and tap again, and here is my triangle. So on to the orthocenter. For the orthocenter, I need to construct the altitudes of my triangle. So I'm going to use this perpendicular tool. I'll tap on the tool icon, and I see my entire perpendicular construction. In other words, I see a segment, I see a point, and I see a line through that point that's perpendicular to my segment. Notice that this segment is glowing. That indicates that this segment is ready to be placed. One way of placing it is to simply drag it and merge it to a side of this triangle. Now, if I don't like this particular placement and I want to merge it to a different side of my triangle, I can pull it off my triangle side and merge it to a different side. All right, so I'm going to leave it here. And now this point is glowing, and I want my perpendicular to go through this vertex. So I'll tap on this vertex. And here I have the first altitude of my triangle. And it stays in altitude as I drag these points. So let's now construct another altitude. I'll tap on this tool again, and this time I'm going to match this glowing segment to this side of my triangle, and I'll do it simply by tapping to merge them together, and then I'll merge this point to the opposite vertex by tapping, and here I have my second altitude. And for my third altitude, rather than merge this glowing segment to the third side, let's first drag this point to this vertex, and then we'll merge this segment to this side. And here we have the three altitudes, and lo and behold, they meet at the orthocenter of my triangle. So this example of using Web Sketchpad tools shows that Web Sketchpad has a consistent and forgiving interface that greatly reduces the need for explicit directions and scaffolding. It allows students and teachers to concentrate on the mathematics of their constructions rather than on operating the technology. With Web Sketchpad, teachers and curriculum developers can create activities in which the tools they provide to the students are tailored to the task at hand. With the Geometer Sketchpad software, one of our favorite activities was to ask students to find multiple ways to construct a rhombus. Students would need to look through the various menus and the tools available to them and decide what collection of them would be best suited to construct a rhombus. It was almost like a treasure hunt. In fact, it was a bit overwhelming. With Web Sketchpad, we can make the experience much more targeted by giving students small collections of tools and asking them to use those tools to construct a rhombus. So here we have a web sketch that consists of several different pages, and on each page we have a few tools that we offer. So here just a segment and a compass tool. And the goal on each page is to see how you can use these few tools to construct a rhombus. Now, it may not be in all cases a very robust rhombus that can be dragged to form a rhombus with different side lengths or angles than the one you start with, but in each case the goal is to see how to at least build something that stays a rhombus when you drag its parts. And these are little puzzles. On each one, we want to see how the particular tools and how the properties of a rhombus come together to allow us to construct a rhombus. So let's take a look at one of these puzzles. Here we have the segment tool, a compass tool, and a parallel line tool. So I know that this has something to do with the fact that opposite sides of a rhombus are parallel, and I'm thinking with the compass tool, that's going to help us to construct sides that are the same length. In particular, if I construct the radii of a circle. So let's start with the compass tool and make ourselves a circle. And let's construct a radius of this circle. And how about another radius? So we have two segments, both radii, both have the same length. And I'm thinking these are adjacent sides of my rhombus. And let's use the label tool to label these points. Okay, so I am going to now use the parallel line tool to construct a line through point B that's parallel to segment AC. So I'll tap on the tool and I see a preview of exactly what I'm going to construct. A segment and a point with a line through that point that's parallel to the segment. I'm going to match this glowing segment to AB and this point to point C. And now I have a line through point C that stays parallel to AB. To continue, I'll use this tool again. This time I'm going to merge my glowing segment to AC and this point to point B. And here I have my rhombus. I'm going to use the segment tool here to construct another side of my rhombus. And let's use it again to construct the remaining side. And let's label the fourth vertex as D. And now I'm going to use my visibility widget to hide some of the parts that I no longer need to see. I'm going to tap on that widget and then tap on the circle and these two lines, and they all turn gray, indicating that when I tap on the visibility widget again, they are hidden. And here I have my rhombus. Now, as a student, when I'm explaining to my classmates how I constructed the rhombus, this is where I would probably want to tap on the visibility widget again to bring those objects back into view to explain how I used my tools. Let's look at one more set of tools. How about this set here? So again, I have the compass and segment tool, but now I have a perpendicular bisector tool. And that's making me think about the fact that the diagonals of a rhombus are perpendicular bisectors of each other. So let's start by using this tool and see where that takes us. Here we see a preview of what we're about to construct, a segment and its perpendicular bisector. So let's just place these two segment endpoints anywhere we like. And I'm going to label these points A, B, and C, and I'm thinking A and C are opposite vertices of my rhombus, with AC being a diagonal. Now my other diagonal is going to sit on this line through point B, and how do I want to construct that? Well, one way I might do that is to use my compass tool, and I'll make point B the center of my circle, and this other point that's glowing I'm just going to attach to my perpendicular bisector. And now I'll construct the other diagonal of my rhombus here. And that gives me another diagonal, and this diagonal is perpendicular to AC, and because BD and BE are equal in length, I have here two diagonals that are perpendicular bisectors of each other. I can then complete my rhombus as I did before by using the segment tool. And as before, I can use my visibility widget to hide those parts that I no longer need to see. And I can also check that when I drag the various parts of my rhombus, it behaves differently than the last one in terms of its movements, but it's a robust rhombus, it stays a rhombus, and it's really cool. I've used very different properties of the rhombus to actually build one. So with Web Sketchpad, we can provide students just a small number of tools for each activity and really focus those tools on the mathematical content that we want students to be thinking about.
In this section of our workshop, we'll use Web Sketchpad features to connect transformations in geometry to functions in algebra. As we do so, please keep in mind the math, the pedagogy, and the cognitive science that emphasizes the value of active learning. If you've used the full URL shown here, you can tap this Teacher Notes button to see more information. So far, Daniel and I have done all the talking, but we propose this session as a workshop, and though Daniel and I are only characters in an on-demand video, we want to preserve as much as we can of the workshop format. To do so, I'll introduce this first task, and then ask you to pause the video, switch to the presentation website, shown right here, and work through the task yourself. Then restart the video, and I'll make a few closing comments and introduce the next task. This first task is taken from Edwin Abbott's classic Flatland novel, in which the narrator suddenly finds himself in a two-dimensional world inhabited by polygons. What would it be like if we were perfectly normal flatland transformations like dilation or translation, and we suddenly found ourselves restricted to lineland, a one-dimensional world? You'll use page 1 of the sketch to investigate dilation, You'll use page 2 to investigate how translation works in the Lineland, and page 3 to investigate the composition of dilation and translation. Please be sure to answer the questions beneath each page, at least mentally or better on paper. Pause the video now and go explore Lineland. Hi, welcome back. I hope you found the activity interesting. I'll review it with you by going over page 3. On page 3, you constructed Lineland by tapping the Lineland tool, and the green arrow works to accept the tool. You added a dilate function and restricted X to Lineland. You applied a translate function to the dependent variable, and you put the translation vector in Lineland as well. And then you measured the coordinates of all the points on the line. So I'll double tap the coordinate tool and find the coordinates of X, the dilated image of X, the translated dilated image, and the vector that's used in the translation. So now we have all the necessary points measured. I'm going to move the length of the translation vector down here, the 1.41. I'm going to make that a nice even 1.5. Why not? And you likely noticed that the name of this translated dilated image is quite difficult to pronounce unless you're a native Flatland speaker. It's actually a very nice name because it tells us exactly who she is. She is the translated image by the vector from 0 to v of the dilated image about center point 0 and scale factor s of independent variable x. So we know everything about her just from her name. But still, it's quite a mouthful. And fortunately, she's not offended at all if we use a nickname for her. And that's where the label widget comes in. So I'll tap the label widget, and we will tap the label of this translated dilated image, and we could use a manual label, just one that we make up ourselves. She might not know who we were talking about, though. We can use a prime-based label, which puts a prime on whoever she is the transformed image of. So it puts a prime on this label to give her indication. It's just an indicator of how many generations removed she is from her immediate parent. Or we can use short notation. And short notation leaves out the fact that the vector is from 0 to v. It just reminds us it's a translation. Now this guy, he is still using his long name, and we can give him just a short family name as well by tapping him, and that short choice is automatically imposed on him as well. So now we have short names for everybody, and you notice that the measurements actually changed at the same time that we changed the labels. So now you're ready to go exploring about how the values work out and what you were able to figure out. I do hope you had time to address the last question here. If not, I'd recommend you give it a try now, because this last question gets at a really important connection between algebra and geometry. It's a critical takeaway, and the next activity is going to contain a spoiler. So it's a lot more fun to figure it out yourself by looking at it now if you haven't already. Onward to activity 4B. Here you'll build on what you did in 4A in order to construct your own dynagraph. These directions are a bit more mathematical in nature. We depend on you to figure out how to follow these directions by using the tools that are available here in the sketch. The big difference from the previous activity is that you'll separate the independent and dependent variables by putting them onto two different number lines to make the whole operation easier to visualize. So pause the video now, do activity 4B, and come back when you're finished or when you need some help. Okay, we're glad to have you back. Just in case you needed help, we'll run through the construction quickly, knowing that you have instant replay available. If you didn't need help, feel free to fast forward to the introduction of the next two activities. The spoiler I mentioned earlier, by the way, comes at the end of the run-through. So here, to construct a dynagraph, we begin with a number line and put an independent variable on it. That gives us a vary x button, which is nice touch. And we dilate that value of x by a scale factor to get a d of x, and we can press the vary button to watch them move. The rest of the construction we're going to do on the second number line, which is going to be where the output of the translated dilated function is going to come. So the transfer tool lets us do that. We transfer the origin down, we transfer d of x down, and putting a new number line through the transferred origin, we have our second number line, and we see the d of x as it's transferred down to the new number line is still the same as the old d of x. So now we can translate that, translating d of x by vector v, whose length is determined by this slider here. So here we have scale factor of 2, vector of 3, and we can see and compare how x and t of d of x behave. Even better, we can connect them by putting a connector across there, use the trace widget to trace that connector, and use the vary x button to create a set of traces that actually give us a way of seeing by these traces how much t of d of x moves as d of x moves. So the way the traces look actually gives us an indication of the relative speed of the two variables. So we have here both the perceived speed by the fact that we can see that t of d of x is moving faster than x. In fact, it reaches the end of the screen and x is only here, and it reaches the other end of the screen and x is only there. But we also have this permanent record that shows the relative speeds of the two variables, which is very nice. Okay, so we're ready for the spoiler, actually. And the spoiler is the answer to the last question here at the bottom of this page, to write a formula for the value of t of d of x in terms of x, s, and v. Check it out. The value of d is 2 times the value of x, so it's related to the scale factor, essentially multiplies the value of x. So this is s times x is the value of d of x, and then the vector adds another 3 to it, so we really have t of d of x is equal to s times x plus v, which sounds awfully like m times x plus b, and in fact we've created a linear function using only dilation and translation, and that's a deep and profound connection between geometry and algebra. So the other aspect of this is that we have a composition of functions here, and it really makes me wonder how much easier it would seem to students, the idea of composing functions, which is even left out of the Common Core as a mandatory thing for students to understand. How much easier would it be if they really understood that, for instance, a linear function is simply a composition of multiplication and addition. And they've been using it since they first explored linear functions. Onward to activities 4C and 4D. Like the last two, these activities are paired. The first is of which ones don't belong Cartesian graph puzzle. Come up with an argument for each of these four as to why it doesn't belong with the other three. And the next one is a dynagraph puzzle of the same kind. Figure out for each of these an argument why it doesn't belong with the other four functions shown. And you guessed it, we'll ask you at the end how your arguments differed between doing it with the static Cartesian graphs and the dynamic dynagraphs. So as you work, please think about your students who would react to these two tasks. How would their arguments differ between the static and dynamic versions? Pause the video now, do both of these, answer the questions, and we'll encourage you at the end to post your answers and comments on the blog site. We're glad you're back, and we'd love to see your responses to the questions, particularly the responses that describe how the function features you used in your arguments depended on whether the representation was static or dynamic. In case you're wondering, both questions really do use the same functions, although in a different order. You'll see the same four functions again in the next web sketch. Let me conclude these two activities by saying that I think dynagraphs should be used frequently, at least until students have learned to read Cartesian graphs with understanding. And by reading with understanding, what I mean is that students should be able to look at a Cartesian graph and imagine from the shape of that graph how the variables actually move, so that they can interpret a static feature like a slope of -1/2 dynamically and envision y moving in the opposite direction as x at half the speed. And that's a real accomplishment that a lot of students have trouble getting to. Onward to activities 4E and 4F. Close this one, close that one, and we'll look at 4E and 4F. These two sketches show two different ways we've invented to relate dynagraphs and Cartesian graphs in the same web sketch. I'll have some comments to make, but not until after you've tried them out yourself. So please pause the video now, look at this first example, explore it, answer the questions, then go on to 4F, look at it, and we'll check in with you again when you've done both those things. We're back once more with a couple of brief comments. The sketch in 4E, as you saw, is a stacked dynagraph on top and Cartesian graph below, with connecting dashed lines that show how the x value is connected between the two graphs and how the f of x value is connected between the two graphs, so that to guarantee that the number on the y-axis here is the same as the number on the lower axis of the dynagraph. The objective here is to improve students' ability to read a Cartesian graph. So we're going to, by showing the Cartesian point and tracing it, and varying x, we can actually see how the linked variables here create the Cartesian graph. And that's the way we want students to be able to read this graph even without the variables being visible. That's what they should be able to look at this Cartesian graph and imagine what's happening with x and f of x, which don't appear in the Cartesian graph. So this is to explicitly link the two different representations. The objective in part F is to blur the lines a little bit more. Because here, when we have this graph coming along and showing us what's going on, here we have the ability within the same sketch to switch it just by rotating the lower axis. It's either a lower axis or it's a vertical axis. We can make it both. And in this configuration, I find it particularly interesting to trace the connector and watch what happens as we vary x. Because the spacing of the traces actually gives a good sense of the relative speed of the two variables at various points in their motion. So we hope that these sketches may be useful to you and your students, and that the geometry-algebra connection might surprise and appeal to them, and that the motion in their dynograph might help them avoid or correct common function misconceptions. We encourage you to use them to engage your students as active learners, constructing, tinkering, exploring. The Confucian scholar Zunzi expressed this well thousands of years ago when he said, "What I hear, I forget. What I see, I remember. What I do, I understand." In section 5 of our workshop, we'll use Web Sketchpad's transformations as the basis for various constructions and proofs, and particularly for proofs involving congruence. So I want to start with the connection between construction and proof. There's no accident that we often talk about constructing a proof. Euclid's proposition 1, in fact, is not only the solution to a construction problem, but is also an existence proof. But often, when we talk about constructing a proof, we use construct in a figurative sense rather than a physical sense, in the abstract sense of give me a logical argument for so-and-so, rather than the real-world challenge of show me how to construct so-and-so. With all that we now know about the role that embodied cognition and conceptual metaphors play in our thinking, we should be putting the construction problem at the heart of the proof, with the logical argument arising from the process of describing and explaining the construction. The construction itself is not an actual proof, but its steps often mirror the proof steps, which still need explanation and justification. Here's an example that might appear in proof without words, the Triangle Sum Theorem. The fact that the sum of the three angles of a triangle are 180 degrees. We can recast this as a construction challenge. Start with triangle ABC and transform it to make angles B' and C' adjacent to angle A and show that they form a straight angle. With Web Sketchpad, we can make the required rotations dynamic. Drag the slider, and you see the actual rotations taking place. Zero, one triangle. Now we're rotating two images, one about midpoint S and one about midpoint T. And now we have the straight parallel line showing a straight angle for the sum of the angles of the triangle. Please go to page 1 to animate it yourself, and then go on to page 2 and build it. In case you have trouble, I'll do a run-through when you come back. So pause your video now and do your construction. Welcome back. Here's my run-through for the triangle angle sum theorem. We begin with the triangle and two midpoints, so I'll double tap the midpoint tool so I can do two, one right after the other. And we need an angle slider, so I'll put the angle slider over here, and I'll make it a little bit bigger so that we can, so it's easier to get the exact angle we're looking for. Now we have two rotations to add to this construction, so we'll use the rotate tool. The triangle is glowing, so I'm going to match that to the existing triangle. This is the center point glowing, so I'm going to match that to this center point right here. And the angle of rotation I want to match to the existing slider. Now let's make sure that this works right. Okay, that does look right. It looks like it's looking pretty good. I should also use the text tool to label the points of my original triangle. That one I can call A. This one is B. I want this one to be C. This one to be S. And this one to be T. So now everything's labeled to my satisfaction. I can make sure by moving the slider that it really does work. We still have to add the second triangle, but we're well on our way. Worth mentioning that the construction itself is not the complete proof, because we're going to have to justify why it is that this segment is parallel to BC from the original triangle. That's an earlier theorem in transformational geometry and won't represent a problem, but I just want to be clear that this is not the proof. This is the steps of the proof, and the justifications have to be generated by students separately. Let's now go on to Activity 5B, Quadrilateral Definitions. The idea here is to explore defining special quadrilaterals based on their symmetry. Might this be a useful, elegant way to define special quadrilaterals? The construction specified on page 1 can be done several ways. There's no one right way to do it. Please pause your video, do the construction, and figure out what type of special quadrilateral you've created. When you return, I'll run through one possible construction. Welcome back. I'll do a quick run through of one possible construction for page 1. Begin with a line and a perpendicular to the line, and I'll drag the endpoints of the given segment to match the points that define the line, and also to put the perpendicular so I don't have extra points lying around. And I'll now reflect this point across this line, and then reflect another point across this line, which now gives me the 4 vertices I need, so I can take the quadrilateral tool and attach its points to my 4 vertices, and I leave it to you to figure out what figure we have just created. Now we'll go on to Activity 5C. This explores the problem with congruence. These slides were created by Jim King and other people at the Park City Mathematics Institute, and they detail some of the difficulties with the traditional definition of congruence for using lengths and angles. Pause your video now and go through the 5 pages. Welcome back. I hope you found the slideshow thought-provoking. I view these slides as a strong argument for basing our definition of congruence on superposition by saying that figure A and figure B are congruent if and only if there's an isometry F such that F of A is exactly superposed on B. Though superposition is an unfamiliar word to students, the idea of an exact fit isn't hard, and they meet it frequently in other congruence-related activities, like the next one we'll look at, mystery transformations, number 5D. I'll demonstrate the mystery transformation on page 3. and then ask you to do several more on your own. The first thing I check is whether the two triangles are same-handed or opposite-handed. What I mean by that is this. If I do an imaginary tour of triangle ABC, going from A to B to C and back to A, the inside of the triangle is always on my right. If I do a similar tour of the blue triangle, from D to E to F and back to D, the inside of the triangle is always on my left. So these two are opposite-handed. I already know that translated images and rotated images have the same handedness as the original. Since ABC and DEF are opposite, the transformation here must be either reflection or glide reflection. No matter which of these it is, corresponding vertices must be equally distant from the mirror. So the mirror has to pass through the midpoint of segment AD. It must similarly pass through the midpoint of segment BE, and although I don't need to construct it, the midpoint of segment CF. Two of these are enough to determine my mirror line, so here's the mirror line from this midpoint to that one. I can see right away that reflecting the red triangle directly across the mirror line is not going to give me the blue triangle, so this must be glide reflection that we're looking at, and I'll choose the glide reflect tool. I match the pre-image to the red triangle ABC and put the vector/mirror on the mirror line that I've already determined. Let me use the style widget to fade out the mirror itself so that I'm emphasizing the view of the mirror/vector, and adjust the vector to see if I can get a match here. Bingo! It works. By the way, I intentionally chose to demonstrate the glide reflection case because it's important for the sake of completeness to include all four isometries. How remarkable it is that there are only 4 kinds of isometries in the Euclidean plane. Now pause your video and do several other pages on your own. Welcome back. I hope you enjoyed the challenges you just took on. We're about to undertake a bigger challenge, the challenge of proving the side-side-side theorem. Side-side-side has traditionally been a postulate. We assumed it because we had no way to prove it. But a transformation approach allows us not only to prove it, but to make the proof construction surprisingly accessible to high school students. The proof is based on the listed definitions and facts right here. In a moment, you'll construct the side-side-side theorem, but first I'll show you the construction steps for the segment congruence theorem. You'll need these techniques doing side-side-side. Besides, if you've ever had students accuse you of splitting hairs by distinguishing between congruent segments and equal length segments, you'll appreciate how this approach clarifies that equal lengths is a statement about measurements, and congruence is a statement about constructing superposition. So our task is to superpose an image of AB on CD to prove that they're congruent. And we'll begin by superposing A on C using the perpendicular bisector to create the mirror such that the reflection of AB across the mirror will superpose A on C. Now we just have to get B prime superposed on D. So let's go ahead and create that perpendicular bisector. And let's do that reflection. And here we go. Oh my goodness, A double prime is no longer superposed on C. How did that happen? If we undo a step, we might realize that it certainly looks like CD here is a little longer than A prime B prime. If they were the same length, this point would be on this perpendicular bisector. That's the perpendicular bisector theorem. Ah, we forgot to impose the given fact. Watch what happens when I click this tool. Segment CD was adjusted. This tool adjusts segment CD so it's the exact same length as AB. Now, this point is on the mirror. We can go ahead and do our reflection now. And there we go. We have established the superposition, which gives us the steps right here that are involved in proving segment congruence theorem. The perpendicular bisector step, the reflection step, another perpendicular bisector step. At that point, we realized we had to impose the given fact, and the last step of the proof is the final reflection. When you reach a similar stage in the side-side-side proof, you'll have to decide when is it most logical to apply the given step of the proof. That's not really a construction question. That's really a proof question of making a proof as logical as possible, as persuasive as possible. Please go to the side-side-side theorem page, which opens the sketch for you. Go to page 2 of the sketch and have a go at proving the side-side-side theorem. Pause your video now and come back when you're done. Welcome back. We hope that using the side-side-side construction as the basis for proving the SSS theorem made sense to you, and that the history icons along the bottom of the sketch were a useful way to structure the proof of side-side-side. Please do take the time to send us your comments, questions, and suggestions by going to the blog page for this workshop. Coming next, Daniel will suggest ways that Web Sketchpad can be useful for both in-person and virtual classrooms.
Now I'd like to show you how Web Sketchpad supports distance learning and virtual classrooms, as well as the wide variety of resources for Web Sketchpad that exist across the web. Teachers and students can use Web Sketchpad to construct, investigate, collaborate, and prove in both virtual and in-person environments. It provides exceptional support for good pedagogical processes. Now, in terms of resources for Web Sketchpad, a really good place to start is right here on this workshop page. You'll see at the top we have tabs for the various units we've created, and you'll find here a very rich collection of activities that include both the activities you've done today in this workshop, as well as many others. Our activities are under a constant state of refinement, so you'll see that they'll change from time to time. And in fact, if you use these activities and find ways to either tweak them or perhaps have an idea for a new activity, by all means email us. We'd love to hear from you. Now, there are other resources on the web that really allow you to make Web Sketchpad more customized for yourself. And these include the Web Sketchpad tool library and the Web Sketchpad Viewer. To learn about both of these, you can go to the Web Sketchpad tool library and Viewer page, where you'll find extensive videos that introduce their features. But right now, let me give you just a brief introduction to each of these resources. Let's start with the Web Sketchpad tool library. The tool library comes with a wide collection of tools that you can add to Web Sketchpad models. Here we see the collection of tools you have at your disposal. For example, I might choose to add the point tool, the compass tool, and the segment tool to my Web Sketchpad model that's sitting here at the top of the page. To do so, I'll just tap the point icon, the compass tool icon, and the segment tool icon, and all three of them are now here and available to me, and I can use any one of them. As a teacher, I might use this tool library to create customized Web Sketchpad models to share with my students. After I've made the web sketch, I can then go here and download it. Once it's downloaded to my computer, I can share it with my students in either an email or on some publicly available server for the school. Now, another use for the Web Sketch tool library is for students themselves to use. You might be giving students some assignments where you'd like them to decide which tools they need to use, or where there might be a need for many tools that students need. In that case, students can come to this page and mix and match the tools themselves. So this library is very handy both for you as a teacher for creating activities, and sometimes for your students as well when you'd like them to decide which tools they'll need. A companion to the Web Sketchpad tool library is the Web Sketchpad Viewer. After students have completed an activity and submitted their files to you, you'd like to have an easy way to be able to view their work. And rather than have to open up each of their assignments one by one, you can actually view them all collectively on this one page. So I'm going to tap Load Sketches, and here I see the work of 8 of my students. And I'll simply select all 8, and I'll choose Upload. And here instantly I see the work of everyone here on this one page. And what I'm seeing here is not just static images of their work. This is actually the real thing. These are dynamic. So I am looking at their actual sketches, and if I like, I can even come here and add to it if I have comments about what they did. So this is not only a nice way for you to be able to easily view the work of all your students, it's also a good way to be having students give presentations, whether virtually or in person. If, for example, I decide that I'd like to have Sarah present first, followed by Nan, I can drag their names to the top, and we see now that they are the first and second here in this collection. So we think the Web Sketchpad Viewer is a very powerful way for teachers to collect their students' work, assess it, and also use this for presentations. There are other sites on the web where you can find Web Sketchpad resources, and by far the largest is the Sign of the Times blog that Scott and I maintain. This blog, which we've been writing for the last 10 years, contains everything from kindergarten through college materials, mostly all of which include Web Sketchpad models to accompany them. So we talk about geometry, our geometric functions work, conic sections, advanced mathematics from linear algebra, for example, all of that here together. And one particularly strong area that I'd like to point out here is the section on our blog where we've collected all of our elementary activities relating to Web Sketchpad. And we have a link for it here. And these activities mostly were all created as part of the Dynamic Number project, which Scott and I helmed from 2009 through 2012. And you'll find here many, many activities that we've written, which were originally designed for the Geometer Sketchpad, but we've converted to Web Sketchpad. So I think those of you who either are in elementary school or work with elementary teachers will find this to be a very useful resource. I should also mention that there are web sketches available on the NCTM Illumination site. And one that we are particularly proud of is our Bunny Times web sketch, which we created to help students think about multiplication. And this by far is our most complex sketch. And it was created by Scott over a period of probably half a year, if I'm correct. And all of these animations here that you see with the bunnies hopping along and the windmill turning, all of these were originally created in the Geometer Sketchpad and then exported to Web Sketchpad. So Web Sketchpad is incredibly powerful in terms of being able to take nearly all of the advanced features from Sketchpad and allowing you to use them in Web Sketchpad. I should point out that everything you see here today, as well as anything you create, is strictly for non-commercial purposes. You're free to use any of the materials on this list, but make sure they're for non-commercial purposes. In terms of commercial uses of Web Sketchpad, I should mention that at McGraw-Hill, we're using Web Sketchpad in many different curricula, including everyday mathematics, reveal math, and illustrative math. So this provides an overview of all of the different resources available to you for Web Sketchpad. Now I'd like to briefly look at the connections between the Geometer Sketchpad and Web Sketchpad. Web Sketchpad stands on the shoulders of the Geometer Sketchpad, and we think in many ways it improves upon it. As you've seen today, Web Sketchpad's user interface is exceptionally clean and simple to learn and use. Each of the activities comes with only those tools that are necessary for the task at hand. Web Sketchpad's tools are also self-documenting. When you tap on a tool icon, you instantly see what that tool will build. This allows us to create activities where we don't need to provide too much in the way of technology instruction and instead can just focus on the mathematics. You've also seen today how easy it is for a sketch author to tailor the available tools to the task, and you can do that by using our Web Sketchpad tool library that I demonstrated in the last section. Web Sketchpad also has new features that are just unavailable in other dynamic mathematics software, and these include function notation, glide reflections, and drag merging. Now, I would imagine that for some of you watching this workshop today, you have a history of using the Geometer Sketchpad, and it's possible you have a large collection of Sketchpad files and are wondering if you can easily use these in Web Sketchpad. Can we convert between Sketchpad and Web Sketchpad? And in nearly all cases, the answer is yes, and it's quite easy to do. If you're interested in learning more about how to convert from Sketchpad to Web Sketchpad, you can email us and we'll give you the information, and you can do this for non-commercial purposes. So Web Sketchpad builds upon the best features of Sketchpad and adds a whole lot more to it that we think makes it both mathematically and pedagogically superior.
Thanks for joining us today. We want to make it clear that we're committed to continuing work both on Web Sketchpad software itself and on high-quality innovative curriculum that takes advantage of Web Sketchpad's features. We're grateful to McGraw-Hill Education for its continuing support of the software, and we're grateful to the NSF for enabling the work of the Forging Connections project, from which many of the activities that you saw in today's workshop were drawn. All of the materials in this workshop video, on this presentation site, on the Forging Connections site, and on sineofthetimes.org blog are freely available for non-commercial use, as is Web Sketchpad itself. Thanks for coming to our workshop. We hope it's been useful for you, and we hope to hear from you on our blog page.